Okay. Hello, everyone. Thanks for joining. We almost filled the entire room. There's a couple of spots. That's great. So we're here to talk about machine learning for microcontrollers using Zephyr and emlearn library, which I maintain. I work for a company called Sound Sensing in Oslo, Norway. We provide sensor systems that monitor ventilation systems for buildings such as this one. We monitor if there's anything weird going on using sound and vibration and notify the building operations team. And for us, Zephyr is an important tool to prototype new type of sensors that we can apply. The goal and structure of this talk. So the goal is that you as an embedded software engineer become familiar with how to develop and deploy machine learning on a microcontroller using Zephyr and emlearn. So the main structure will be around a kind of case study or example application of activity recognition using accelerometer or IMU type data. And we'll go through some, we're not able to do all the phases of a machine learning project, but we'll cover some most relevant here. Reading of sensors, we need to create some data set, we need to train a model and deploy a model. That kind of closes the loop. And as a bonus, we'll cover a little bit of MicroPython. So what do we use machine learning for in an embedded or a sensor or microcontroller type context? The primary application is automated sensor data analysis. So we have, in these kind of systems, can be represented like this, can be many different types, but we have some sort of sensors that can give us usually a kind of a raw data stream of sorts. Can be quite rich, can be specialized, can be general purpose. And then a microcontroller system that will run our code, including then a machine learning model, a trained model. So we are not so much doing learning on the device, we're usually doing inference. So we'll train the model and then deploy it onto the device afterwards. And then this model will help us extract the relevant information in that data stream, so that we can, for example, act on it directly, maybe with a motor control, or we can pass on just that relevant information onto a network, be it wireless or wired, or maybe over some legacy bus, like in a building system or serial or something like that. And the benefits of doing this machine learning inference on the device, on the microcontroller, is that you can build standalone systems that have low latency, so they can have guaranteed latency, including real-time guarantees. You can have highly power-efficient systems because sending data is usually one of the most power-consuming parts. So the more you can reduce the data you send or how often you send, the better. You can have systems that are more privacy compatible because you can avoid sending the potentially sensitive data onwards to a cloud system. And you can also build systems that are quite low cost because they no longer depend on an external system. And microcontroller and MEMS sensors have become very, very, very low cost. But this requires us to fit into that system and to handle all the parts of a typical machine learning project. So there are many applications of this that span basically the whole gamut, anywhere where you could see a microcontroller. You might these days today see at least some applications where you're doing a little bit of DSP and you may be doing some machine learning. So in consumer technology, if you have a fitness watch, smartwatch, etc., their sleep tracking or their activity tracking, etc., that will be a small machine learning model that does that. Or in these kind of home assistant type devices, or on a smartphone, that keyboard spotting, hey Google, hey Siri, etc., that triggers the system that's usually running on a dedicated microcontroller or a similar grade system, and then it wakes up the rest of the system. And in industrial applications, yeah, we monitor ventilation systems. There are many such things around predictive maintenance. There's also monitoring for animals, for example. Or it's also just interesting to make fun things with it. So this is some examples that I've seen people do. At the bottom is like a magic wand, so you can cast a spell to trigger whatever action you want in your smart home, right? Why do the boring thing and just have buttons? Or you could create a smart doorbell which lets in a cat only if it's your cat and it does not have any gifts with it, right? And there's no end to that, what you can do. One challenge in this setting is that we have kind of two worlds. We are training our model on the PC. We want to use the established tools from there, which is usually Python, etc. And that will be used in the training process. And then we run on device. That needs to fit the constraints of the device, which usually means something like C, C++, etc. Very low amount of RAM. And the challenge becomes not only you have these two worlds, and sometimes people that don't talk so much the same language, but this also needs to be compatible across. If you make any mistakes, especially in your pre-processing, your model will be fed data that is subtly different, and that will cause your model to fail. And in many cases, it might just be a little bit off or off in some edge cases, and that is very hard to detect. So you need to have quality assurance. And this is where portability is very important. So being able to run the code that you have on device also on the computer. And this is an area where Zephyr is very strong. You can basically run all of Zephyr on your computer. And then you can take pieces of that C code that's portable and also use it directly in the pre-processing part. This is very valuable. So in these cases, or on these type of devices, we might be interested in anomaly detection, so figuring out if something is not as it usually is. Or classification is probably the most common. Also, our example is determining what is this what is happening right now in terms of a category. We'll kind of be able to categorize things. And regression, where you have some sort of continuous response. And all of these are supported by the emlearn tool, but we'll focus on classification. It's the most common and also a good basis for understanding. So in activity recognition, there are multiple ways, but we will use an EMU, an accelerometer combined with a gyro for this task. And there are many variations of this task, but they all usually have some sort of structure like this. What we're interested in is using the accelerometer to determine some classes of interest from motion. So this is for the fitness tracker, etc. So the classes that we output might be something like this. This is what's called like everyday activities. I can give you a rough understanding of, for example, how much physical activity you have during a day. And this is like standard functionality on a fitness watch or smartwatch these days. And there's these different steps. We'll go a little bit more in detail, and that allows us to realize this kind of task. A key part here is that we are classifying or processing in essentially an infinite stream. There is no end to the motion data that comes in. So we chunk it up into reasonably sized windows, and they are usually processed independently through the models. And there's usually some sort of pre-processing or feature extraction step, which takes the raw data and makes it into something a bit more chewed up, ready for the model to do its thing on. And then the model will output a class in this case. And the task here is there's many like variations. So basically, to a large extent, up to the data set that you have, which particular task, particular classes that you will be output. So you could, with this that I'm showing today, you could easily make an exercise tracker that says which kind of activity you're doing and for how long. Or you could, I made a toothbrush timer, which counts the time that you're actively brushing your teeth so that you hit your 2-minute recommended mark every day. If not, you get a very sad sound from the device, and then you have to do it again. There was a master student, this is also now deployed in the field from others, doing health monitoring of cattle using the same kind of technology and approach. And in that paper, they show that doing the model direct on device is around 50 times more power efficient than transmitting the raw data. So one key aspect that we'll need to do kind of at the start of our process, we cannot do machine learning on data if we don't have any data. We need to read sensors. And we need this kind of, if we want what we we don't care about each individual data point, which might be like at 100 hertz or something like that. We care about like a bit larger chunks of time. So for example, for activity detection, you might chunk it up into 4-second windows, and then you compute them with overlap. So you compute a new, or you look at the latest 4 seconds every 1 second, for example. You might have a 100 hertz sample rate, maybe it could be lower, so you typically have a sample interval of around 10 milliseconds. And you want to be able to have a reasonably powerful model, so maybe you would set a processing budget of 60 milliseconds for this entire window. Note that the budget that you might want to have is larger than a single sample, so you need to be careful when you do the processing to not exceed the budget. We're a little bit cropped, okay. So the easiest way to get started with this on Zephyr would be to use the sensor API, what's called the fetch and get API. There are two kind of variants of the sensor API now. And this is for getting a single sample at a time, which means we would need to do it at 100 hertz. To get 100 hertz sample rate, you trigger a readout from the sensor using sensor sample fetch, and then you will get all the channels of that device. For example, if you have accelerometer and gyro, that means you have 6 channels, X, Y, Z, and the 3 rotation channels. You just get all that in. You need to do some internal buffering, and then in this case, put it into a queue. So this would run on a kind of a like medium to high priority thread, which really runs at that tick rate that we're interested in sampling. And then once we have a ready for 4 seconds or a couple seconds buffer, we'll pass it into the queue. And then there's another thread, which is the application thread that can, just look and sit and wait basically and check this queue from time to time. And once there is data in that queue, that is a complete set of data. So you can just pass that directly through the pre-processing and your model classification. So this kind of structure makes the application code nice and simple. And most importantly, we are still prioritizing and sampling at this exact sample rate. However, this strategy, it's very simple, it's universal, so that's the great part of it. But this means that the CPU cannot sleep much because we have this high priority loop that needs to go over 100 seconds. And if there is any variation in the scheduling in that thread, we will cause some jitter on the sampling, which is not ideal. So what would be a better way? So this works and fine, and I think in practice this will be okay if you're not so super power constrained, but it's not the best way. A better way is to use the first in, first out buffers that are present in basically all IMUs these days. They might have the capacity to store maybe 32 samples, or some have up to a couple of hundred samples. And if you would have the same 100 hertz sample rate, that means that you could wait up to like 320 to 1,280 milliseconds in order to service it. So that gives you a lot of time that you could do. If we were going to spend like 60 milliseconds on our machine learning model, we can easily fit that into there, even though our application is doing other things at the same time. If we do this, we could basically drop that high priority thread and do it directly with our application thread. So, and an important benefit here is that now our CPU could sleep. So we could just wake up every, say 500 milliseconds. The rest of the time we're just sleeping, and the buffering happens on that device. And they're incredibly power efficient when they do this. And we also get perfectly sampled data. There is no, our code does not influence the sampling intervals. So we have very nice regular time series. And also that we have fewer threads can be a nice benefit and simplification. This approach is quite simple to implement. If you do I2C or SPI, you need to enable the option when you configure the sensor, but otherwise you just need a way to tell how much is in the buffer and a way to read kind of a whole chunk. And if you want really long context windows, maybe you would have kind of 2 levels of this, where you would put it into a bigger buffer to get that 4 seconds, for example. But this does not support DMA. There is a new API or family of API in the Zephyr sensor module, and which is called read and decode. I think it was introduced in 4.0 maybe. And that can utilize the FIFO devices in these accelerometers directly. That's usually done on the driver side. So it means your application doesn't need to care about the details of that, which is nice. It does make the driver a little bit more complicated. And it can also utilize DMA. So this is all like built kind of on a async first type API. But it does mean that you need RTIO support on your Zephyr platform. Otherwise, you cannot use this. There is a good example of how to do this in the Zephyr documentation. Right now, I only found 18 drivers that support this new API. So this is kind of like the recommended way forward. But right now, there's not that many compared to everything. So it's something to, if you're doing something new, you probably want to look at this. So if we can read data, that's a good start, but we'll need to create a whole data set. And one simple way of creating a data set for this type of application would be to do a controlled data collection. We basically say like, okay, I'm going to do this, say it's exercises. Okay, now I'm going to do lunges, which is like, you'll indicate that before you start the activity, you indicate, okay, that's what I'm going to do. And then you start the recording, you do that activity continuously, and it just continues to save devices onto the file system. So having a file system, which is not like always so well supported or standard in embedded systems, is super nice. And Zephyr has great support for file systems in general, be it FAT, little FS, etc. It's usually easy to enable, whether it's on the SPI flash or SD card or internal in your flash, etc. And then it also has great support for USB mass storage. So, and I find that a very convenient way to just store it there and then be able to copy it over to your PC later with no special tools. An alternative, some devices don't have USB, or maybe you want to have it wireless. There's, I don't remember, it's called symbol management protocol or something like this, server available in Zephyr. And that allows you to do file transfer with standardized tools over many different transports, including serial. So if you just have a serial, you can still have this kind of convenience, which is nice. And in emlearn, there's a CSV reader and writer now, and I'm working on a NumPy reader and writer, which is useful, just like common formats for this kind of sensor data. So that labeling would give us very rough indications, right? But maybe we didn't complete the activity the whole time, or we took a little pause or something like that, might give us not the best data. So a good way of doing data, like proper labeling for this type of application would be to record yourself or the person that is doing the activities with a video camera on your phone or any other video camera, and then to use that as a reference for labeling. And I like to use the Label Studio, and then you can play off the video, and you can import also the time series. And you need some way of synchronizing this, same like challenge as the audio people have when in Hollywood, where they have like a clapper. But in this case, I would like tap the device like 3 times or 5 times, and that's what I marked in the start there and at the end, so that we have some sort of way of cross-referencing our video, which comes from another device, and our sensor data. And with that, you can then label in that timeline, and we can make sure that it all lines up. So this would give us very rich and strong, what's called strong labels that have a precise time of the start and the end of the activity. And Label Studio is super nice for this, because you can also now import time series. So you can have some energy indicator or something like that, which can help you like move in the video much faster and to label the relevant parts. And there are some tools for this in the MicroPython repository, which can also be used for C. for like creating the kind of format that Label Studio expects, etc., and then the other way around when you want to put into training. Yeah, about training. So once we have a data set with suitable labels, because that's the key to machine learning, you need data, but you also need labels. You need something that we human or some way of knowing that what the data is. That's what the machine will learn from. You want to do some pre-processing. For activity recognition, you can, for simple things like my toothbrush tracker, you can get away with very simple things, like you try to separate the gravity so that you can have some sort of feature that is which angle is the device being held at. And then another feature which indicates something about the motion, like in which direction is the motion and how is in intensity, etc. And for that, you can use simple statistical summaries. This is some Python code implemented the same in C for Zephyr. And that can go surprisingly long way, actually. And there is some start of some example with Zephyr integration in that repository. And we do have, for this task, since I've used it as an example in many cases, there's a full pipeline, training pipeline for that. But that is already built, that one can use directly, import the dataset. But basically, it's kind of, if you are from data science land, if you're a machine learning engineer, it will be a very standardized and familiar process. There will be some data splitting. There is a random forest classifier, which is from scikit-learn, a very popular library, and some way of doing hyperparameter search. And hyperparameter search in embedded, you also want to take care of performance of the size of your model. So there's some examples in emlearn how to do that. To look at because you can always get, or you can often get higher performance, but at some point it might be that you increase your energy expenditure by 10x by just gaining a small bit. So you want to look at the Pareto front. There's some examples for that in the repository. Yeah, we can use that in this case, or otherwise you would need to learn. So once you have a model that is trained on your computer, on your data set, and you check that it does like reasonable job according to the metrics, then you can deploy it onto the device. And this is where emlearn specifically is the tool that converts that. So it's available as a Python package. And then in that training pipeline, you would import emlearn. And your model will be like a standard model, like a scikit-learn or Keras or whatever framework you're using. And then there's a one-liner that converts that into a C model. It's a representation of what will go onto the device. And you can then save that to a header file, which is generated, and you can include that into your build. Here's an example for a simple neural network. And it's similar for trees, etc. All the models supported. And to get it into Zephyr, I mean, it's a header-only C library, so you don't need much magic to do it. But as a convenience, there is a Zephyr module, so you can just declare it in your West config. You enable it in your project, and you can then it will automatically do the correct include paths, etc., so that you can use it in your code. And we also test, so I have automated tests in the emlearn repository that tests against Zephyr, so that we know that we don't, for some reason, break something that would affect Zephyr. There's a little bit of docs around this, but basically this is what the docs say. It's very simple to do, and it's now also mentioned in the official docs from Zephyr. So, and using the C code is quite simple. You include it. You will need to do some pre-processing. So that is usually application specific. I have then an example for the task that we showed, but that's on this bottom left. And you would then pass this features to your model. It will give you a classification. Or there's also support for probabilistic output. So you can get like the probabilities that it is a particular class. And then you would do something with that result. And this very simple example was just showing some text on a screen. But there's also Zephyr is very powerful, right? There is so much facilities, for example, for wireless communication, be it like Bluetooth or Wi-Fi and other kinds of networking. There's also support for screens, etc. So so you can use all the familiar things from Zephyr there to whatever is suitable for your application. emlearn supports not all the machine learning model in the world, but it will support a decent selection that is relevant, particularly for embedded devices and that are quite simple and effective, including some neural networks, but also some classic methods that are still very relevant for many applications because they're often more power efficient or might have some good properties with terms of robustness. So to kind of bring that together, we saw how we could read data from our sensors with the Zephyr. We saw just a little bit about pre-processing, how to load a model that has been trained on our computer, load it onto the device. And we haven't discussed much about post-processing or output, but that is generally quite general. So then on to so that was the key part. Like we went from kind of having an idea and showing all the pieces. I did not cover much of validation. If you're interested in that, like how do we validate and do the quality assurance, come talk to me later. As a bonus, talking a little bit about MicroPython. So I mentioned in the start that one of the challenges with machine learning in this space is that you have the firmware developers and that ecosystem, which is generally C or low-level languages. And then you have your machine learning engineer, your data scientists, who are working in Python and the related ecosystem. And that needs to all be compatible, and both in terms of the kind of communication and social aspect, and in terms of the technical part where you might need to implement things twice into different languages, etc. That can cause challenges. So one way of trying to bridge this gap for some applications would be to use Python also on the machine, on the device, on the microcontroller. And that's the motivation, is to kind of try to do these combined projects in an easier way. So MicroPython is an implementation of Python for microcontrollers, implements a subset of Python 3, and it runs on devices with 64 kilobytes of RAM or more. And it supports Zephyr as a hardware abstraction layer, so you can run on top of Zephyr. And there are multiple other ports as well, but the Zephyr's port has matured a lot lately. So it's something that if you're interested in Python or scripting, get those benefits of interactive or rapid prototyping, it can also be useful outside of machine learning, then this is something I think you should check out. It's existed for just around 10 years now, so it's a pretty, in general, MicroPython is a very mature solution. MicroPython and Zephyr together is not, at the moment, super mature. That's maybe someone want to contribute, help test, but it's rapidly developing now. One cool thing with MicroPython is you can also use C, so you can do a combination, and this is very powerful because you can do your code in Python. If it's fast enough, that's great, you're done. If it's not fast enough, there are many tools, but one of the tools is to write some of the code in C. And then it would expose a Python API. So the application developers can use a nice convenient Python, but you can still have the efficiency of C, both in terms of execution speed and memory and program size. And you can install these at runtime, which I think is a fascinating or super powerful tool. And we have a start of so the C API in MicroPython is not the same as on Big Python, so like the C Python, which runs your desktop. That means that you don't have the standard libraries, but we do have compatible versions of them to a large degree, including a wrapper for emlearn and ulab, which is for NumPy, etc. So emlearn MicroPython is then MicroPython bindings, and we basically expose all the existing C things to MicroPython. And it is, yeah, of course, quite a lot faster than doing it in straight Python. And using it is very similar as to in C. Here we usually load the files from disk. We're kind of like a little bit more high level, so we would load the model definition usually from a file system. MicroPython basically always comes with a file system included, and also has tools, standard tools for dealing with such a file system. Yeah, there's the part of loading the model, and like this is essentially the same as in C, just like with a slightly different language. In the emlearn MicroPython repository, there's also a bunch of examples that can also be relevant if you're developing in C, because these like show the general approach. So there's a complete example for an activity tracker type device, which I talked about today. There's also sound processing with noise monitoring and image classifier examples. So, and those can be like, with a little bit of work, you can kind of backport that to see if you're interested in that. So to summarize, machine learning inference, so running a trained model on the microcontroller, is useful for many applications. And Zephyr is a good base for this, especially because it has a sensor API with a lot of existing drivers, and you need some sensor data in these kind of systems. It also provides kind of high level and useful utilities, such as a file system, so you can save data, load data for validation, and excellent options for connectivity. And emlearn is a library to make deployment of trained models simple by converting scikit-learn or Keras models into efficient C code. And it's easy to use in Zephyr via the Zephyr module. And I talked a little bit about bonus, how you could use MicroPython together with Zephyr and emlearn MicroPython. Yeah, there's documentation. I've also given presentations related to these subjects several places, with usually a little bit different angles. You'll find them on YouTube, etc. So thank you so much. Do we have any questions? Yes. Yeah, I repeat the question. Does emlearn support quantization? It depends a little bit on the modules. So CNNs support quantization and random forest, etc. We don't at the standard neural network right now, because there's so many other tools that do it, like TF-Lite Micro. So check it, your favorite model, if it's there, and if not, there are. Yes. Do I support Helium or Neon or these kind of extensions? At the moment, no. And I'm not really planning to, because they are device specific, and the type of applications we focus on usually don't need it. So we're prioritizing the simplicity over that. And it's all going to become even more complicated when we get these MPUs in our microcontrollers, and there will probably be 79 different versions of that coming out in the next years. There was another one in this area. Yes, if I support versioning of models or a way to easily deploy a new one. The majority of the kind of inference implementations have two modes. Either what we call inline, which will generate C code, and that then you would need a way to load C code, like MicroPython. But most of them also support what we call loadable mode. So that is a way that there's a in-memory data structure which represents your model. You can build that up. And we don't usually have a standard way, like file formats for etc. But so if you just decide how you want to store it, and then you can build that model up from a file. Yeah. There's a question there. Yeah, so the question is, have I found any gaps in the Zephyr ecosystem, and what could be things to improve for these kind of applications? So, well, the part about the sensor API, that's already been addressed, and the better handling of larger data streams or batch data streams. That's all already going in a right direction, so that's great. I found that there is something called the Zephyr Scientific Library, which is under the Zephyr project that has like sensor fusion algorithms, but I don't see much documentation for them or much mention of them in Zephyr. So that could be a thing too, because there looks like there's the good stuff to integrate gyro and accelerometer looks to be there, but it doesn't seem very well documented or utilized. Yeah. If I'm willing to maintain it, yeah. Yeah, but so there's pieces like that where that could be very useful to at least to try to reactivate it maybe or something. I don't know. Apart from that, I think it's generally quite good. I mean, the facilities are quite powerful. But yeah, documentation. We could have more application-oriented documentation, I think, around these topics. There's a question in the back. With the emlearn, Orange. Yeah, so the question is the MPUs, can they be used? emlearn does not support MPUs. They're not really planning to. It's already complicated and it's going to get more complicated as a mostly me project. I'm not going to commit to that. Portable C is great. Make compilers that do it for me, please. But yeah, I think ST has quite good support, or one of the first ones out now with the MPUs. And with Helium, when that becomes available, I think that's going to be quite accessible via our SimSys, etc. So there are many options for that. And if you really care about the high performance things, probably TF Lite Micro is a better option than emlearn, because it focuses more on that, like heavier applications. And there was one there. Yeah. Yes, if there's been much use of machine learning on Zephyr. I have not seen anyone except for Benjamin and his electronic notes. But this is a thing, like I've been involved now since 2018 in this TinyML space, before some of the bigger projects like TF Lite Micro, etc. And everyone was saying it was going to be next year. Well, and that's 6 years ago now. There's applications out there, but they tend to be the ones that are really successful are in these particular niches, like the keyword spotting, etc. And that usually forms like people don't call it machine learning anymore. It's just like keyword spotting. Here's like how to do that. And the vendors, for example, etc., they will provide like full examples to do that and not much else. So like you get this bimodal thing where like particular applications will be super well supported, and then things outside is like, not much done about it. Computer vision is in a similar space where there's like particular applications, end-of-line testing, etc. Like has like massive ecosystems and tooling, etc. And then like the other application is like, yeah, well, if you know all the things, you could do it on your own. Best of luck. And we don't see so much. So it's a bit, but that's not Zephyr specific. Yeah. There was another question, but I forgot where. There. Yeah, where do machine learning make sense, and where could simple filters be sufficient? I think that this is very much a continuum. Like you do DSP things in machine learning, and you could do vice versa. I think the one thing that's very useful, even if you're doing very simple things, is the empirical mindset of doing machine learning, where you collect the data set, you label like this is that thing, this is that thing, this is correct, this is wrong, etc. Because that allows you to, even if you hand coded the entire algorithm, like with some filter or it's some thresholding and some hysteresis and whatever classic stuff that can really work, but you need to get those things right. And just with like the space of data that a sensor device is exposed to is usually very big. And so you want to know, am I handling all of them? Do I have edge cases? What is a good trade-off, etc. And then just like, it doesn't have to take more than a few hours, but that collecting the data set, labeling it, make sure that you have a definition of a correct. Often just the discussions in a product team about, is this the behavior we want, or is this the behavior we want in this case, is very useful. And then that labeling activity usually drives that kind of discussions much earlier, which is very beneficial. So I would say, if you have this kind of data, let's say data to decision type problem, definitely put on that hat, look at the best practices and do that. But then, like, yeah, implement it however you like. But it's usually good to be able to have some good metrics, measure how good you're doing, etc. Yeah.
You mentioned that in training the model that it was also important to keep an eye on the power usage of the device. So how do you devise a feedback loop? Because that's something that you didn't measure at that point in time. So is that really deploying a model? Well, how do you approach it?
Yes, power consumption, how to make sure that it's good. So often one just collects data in the first rounds at least, so there's no model involved at all. That will, of course, already tell you something about power consumption, because your sensors will have particularities, and how you're reading the data can influence power consumption. So that will give you the baseline, and you check that against your budget. Do we have any? If you already have problems, well, you don't have a model problem. You have something else problem. But then you can estimate a bit, basically from how many floating point operations you do. But it's quite easy to deploy and then run the test. And you would use the usual profiling tools that you would use for connectivity, etc., like a Nordic Power Profiler, in order to measure that. And what you might want to do is you want to make a few measurements for like maybe the biggest model, or like a biggish model that we can fit, and the smallest that could possibly be relevant. And you can do a couple of measurement points, and you can quite easily you can see how this relates. And then once you've established that, you can integrate this in your training loop. So we say like, okay, I know that I can fit this type of thing, but in terms of power, I need the number of floating point operations to be below a certain limit. Or power is usually not a hard, or there maybe it's a hard constraint, but it's often like a soft one you want to trade off. And then there's like, you want to look at the Pareto front to see like how does that curve develop as the model gets larger. Whereas RAM and Flash, they are usually more hard constraints. You just said like, okay, no matter what, model is not allowed to use more than this, because often you budget that for the model, and then another team, the one that do networking or the user interface, they get another part of your space.